Yes. Okay. 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 Where, Nikhil, Nikhil, where are you now? So much sound is coming. Main road, main road. Yes, yes. Okay, 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 okay. Okay, okay, no problem. I think 40, 47 students. Okay, I think we wait for 2, 3 minutes, then we will start. Okay, Dave, what about others? Only 50 is there now. Out of 72, they are coming. Now time is 11:05. Already 5 minutes. Okay, shall we start the class now? Yes? Yes, ma'am. Okay. Okay. See, listen. They will come one by one. Oh, I think 53 is there now. Okay. See, listen. Today, I think yesterday we discussed both PN junction diode, how that PN junction is formed, then how the energy band diagram is varied with respect to that thermal equilibrium. What is the energy band diagram? Then what is Schottky imperfection and Schottky junction and ohmic contact, etc. Okay. Then the lecture 10, that is lecture 9. Lecture 10 is problem, but the problem is not related to these topics, that is theoretical topics. So that's why you shifted to lecture 13. So 11, 12 already you know. The lecture 11, 12 is a practical. I think almost already completed 6 experiments. Okay, now. Then I go to take this lecture 13. Okay. The semiconductor material for optoelectronic applications and photo current. So that photo current is a part C type question, 12 mark question. Okay, photo current in a PN junction diode. These two topics you go to discuss today. So first, move on to the next. That is where that semiconductor materials they are using nowadays and what type of applications they are using. Okay, anyone, please, anyone tell me what the devices that up to electronic devices, okay, in our everyday life by using that semiconducting materials. Anyone? Anyone? I think nowadays we are using all the electronic devices. There's
Sir,
no doubt.
amplifier.
Solar. Solar cell. Okay, that is application of p-n junction diode. Okay, panel. Yes. Okay.
Sir, amplifier.
Amplifier. No. Okay, then others. Any other? Optoelectronic applications. Okay. Anyway, I will discuss one by one. First, you go to see the first slide. Okay, photodiodes. Okay, see that is already in the title. Yeah. Okay. See, the semiconducting material. Most of the materials, semiconducting materials, falls on the group 3 to 5 and 2 to 6. So in the periodic table, you go to see the periodic table. I think the next periodic table is there. So what type of materials most probably they are using for optoelectronic applications, especially where they go to use for optoelectronic devices, converting that electrical energy into light energy. See here. Okay, the most of the optoelectronic devices applications to convert electrical energy into light energy conversion and etc. Okay, so these materials where in the periodic table you go to see that in the periodic table in the group 3. So materials see here that aluminum, gallium, indium, and here that the group 4, 5, nitrogen, phosphorus. So okay, arsenide, antimony, bismuth, and these materials. So along with these materials, okay, the metals also they are using the group 2 materials also, especially for zinc is a very important application here. Zinc selenide. Okay, so these materials is used for optoelectronic application. Okay, see here the column, the third column already I told. Okay, aluminum, gallium, indium, and here nitrogen, phosphorus, okay, arsenide, antimony. There are so many materials they are used. Okay, except germanium and silicon, not only germanium, silicon, all other materials also they are using for, especially for optoelectronic applications. So where they are using, okay, you go to see one by one the name of the devices and the material, which material they go to use, and you just remember whether you see the materials or not. I think most of them is familiar with the light emitting diodes, LEDs. Is it correct? Say yes or no.
Yes, sir.
Yes. So the light emitting diodes nowadays in the road signal, you go to see the main road, and the most of the signals nowadays is replaced by LEDs only. Is it correct? Yes.
Yes, sir.
Yes. See, those days only that arrow mark they put, the colors are coming now. But nowadays, more all the signals, the entire the signal is that is LED. That green, how the green color is coming. Okay, red color is there. Okay, green is also there. Yellow is also there. So different color combinations LEDs are coming now. Okay, these materials, see here, that aluminum, gallium, arsenide, or gallium, indium, arsenide, phosphorus. There are so many materials. Okay, see here. So all are the transition materials under the group 2 to group 5 and group 2 to group 6 materials using for the optoelectronic applications. So LED, what is the basic principle? I think LED, the next lecture, the LED is coming. Okay, that time I will go explain later. Okay, and the basically LED, which one is converted into light energy? Yes.
Electrical energy.
Electrical energy. Okay. The concept is okay, very simple concept. So the light emitter and modulator. See that aluminum, gallium, arsenide is there, and the gallium, indium, arsenide, phosphorus for optoelectronic application, and LED. See in that road, I think in the traffic signal you listen. What are the color? Different colors are coming. Anyone? Whether they all are same LEDs or different LEDs?
Different
LEDs. Okay, made up of materials that band gap is also there. Please understand the band gap already studied. Okay, according to that, for example, that E is equal to H nu, that is equal to HC by lambda, and that lambda is nothing but HC by EG. Okay, HC Planck's constant, C is okay constant. You know that depends upon your that EG energy gap between the semiconducting material you get the color combination, that visible light 400 to 700 nanometer. Okay, so the visible LED red color is coming where aluminum, gallium, indium phosphorus, gallium, indium oxide phosphorus, optoelectronic, and gallium oxide phosphorus, the normal visible light, visible LEDs. And similar again, the aluminum, gallium oxide, antimony, that is same light emitting diode with a detector. So, so many applications are there for by using these type of materials. By using these type of materials, so nowadays the n number of electronic devices, especially for the semiconductor devices, are coming here. See, the suitable choice for the materials based on the quantum dimension, that is 1 or 2, 3, and 1D, 2D, or 3D dimension, and the range. They are having the wide range of up to electronic properties from where that IR to EV, infrared region to ultraviolet region, and this can be easily turned out for a different band gap. That's just what I told. That depends upon the band gap, because where lambda is equal to HC by EG, that depends upon purely because HC both are constant, where wavelength is directly inversely proportional to band gap. So depends upon the band gap between the materials that the color combinations will come. Okay, that's why they are giving here that easily turn to the different band gap by incorporating magnetic ions or some materials, and they have very strong polarity due to their ionic bonding character also. Okay, now I go to show some of the materials here. See the zinc, some important materials combination, zinc selenide. So that is blue and green LEDs are coming, and the zinc with the sulfur. You go to take ultraviolet emitters, that is in the displays, and zinc oxide, cadmium sulfide, cadmium selenide. So these materials are for different color combinations here. See the color LEDs, short wave LEDs. Okay, and one more tabular column is also there. That tabular column shows, see here, what type of materials they are using and what is the wavelength range. So where they are using. See here, color. For example, the infrared color wavelength is 880 nanometer. So that 880 all are nanometer. Yes, sir. Class some. Okay, 880 nanometer. That semiconductor applications. What are there? They go to use composition, gallium, aluminum arsenide or gallium arsenide. Sometimes you get gallium, aluminum arsenide, antimony also. Okay, and most of the color combinations are coming here. See here, and the corresponding wavelength is given in the nanometer range. Nanometer range, and what type of color combination they are coming here: infrared, ultraviolet region, ultra red, super orange, orange, yellow, blue color. See, there are n number of combinations are there. Silica carbide, indium gallium nitrogen, indium gallium nitrogen oxide, like that. Okay, so these are the materials, composition materials, composition semiconductor composition materials. Corresponding wavelength is given and color also given. Okay. Yes. Are you understand? Say yes or no.
Yes, sir.
Yes. See, for example, if you go to see the traffic signal, whether the green light is coming, you go to see which color, the pure green, 555, and maybe that is made up of gallium phosphorus. There is no doubt. Or whether the yellow color is coming, that is 585 nanometer, that is also gallium arsenide phosphorus. Go to see here, GAP, gallium phosphorus or gallium arsenide phosphorus. And the red color is coming, so red, pure red is coming, super red is coming, that is again the same combination, aluminum, gallium, indium, phosphorus. See, and see these combinations are different LEDs are formed and different color combinations are coming. Okay, nowadays most of the cases they are using LED lights, LEDs. Okay, the different type of LEDs also available, that discuss in the next class. LED the next class. This is the color combinations and the corresponding material, which material they are going to use. Most of the cases they are using, see, gallium. Almost all the cases the gallium is there. Is it correct? See, yes, say yes or no.
Yes, sir.
Yes, because when you go to choose means that is the carrier density, the number of carrier density is far greater compared to silicon and germanium. So that is the reason nowadays they are using. So the gallium is one of the most important material, semiconducting material. So carrier density is the number of electrons per unit volume or number of holes per unit volume is far greater compared to germanium and silicon. Okay. Yes.
Okay, sir.
Anything else here? Any doubts here? That so these are the
Sir,
materials, optoelectronic materials. Okay, the semiconducting materials for applications, optoelectronic applications.
sir, what is CT?
What is?
CT.
No, that is so here that bracket that is in the corresponding Kelvin temperature. Okay, the cathode tube they are using that cathode tube with a very high temperature. You get this combination that incandescent lamp, plain white or cool white like that. The cathode rays tube,
Okay, sir.
CTs. Okay. Anything else here? Anything or any doubts here? Okay, I think then you move on to the next one. Okay. So next, guys, very important topic is a photodiode. Yeah. Okay, what about photo? Photo means photo.
Light.
Photons. Yes, light. Yes, correct. Light, photons. Diode. I think you know diode. PN junction. Nothing but that is PN junction. So this is photodiode. So definitely the light energy is converted. There is no doubt. Okay, light energy is converted into electrical energy. Please understand. In the photodiodes, the light energy is converted into electrical energy. That is the basic principles of photodiodes. So you just go to separate into photo and diode like that. Okay, photo means photons, light. There is no doubt. Definitely that is a light. Okay, then diode. There is no doubt that is PN junction diode. PN junction diode. So now the photodiode is nothing but a device, or it is a semiconducting device. This is a semiconducting device. There is no doubt with the PN junction. Okay, so definitely in between the PN junction, the layer is there. That intrinsic layer is also present, and this is converted to your light energy into electric energy or some current, useful current, electric current. So that is the basics of the photodiode. Okay, and it is also called detector. Also, photo detector. You go to detect, or the photo sensor, or the light detector. Okay, and it operates mostly in the reverse bias condition. So yesterday you see that the Schottky junction and the ohmic contact. Okay, the PN junction diode. Okay, is both in the forward bias as well as reverse bias. What happened? And this photodiode or photo detector is especially for a reverse bias condition. That means your P is connected to negative and N is connected to positive terminal. See here, P side of the photodiode is connected to negative of the battery and N side is connected to the positive terminal of the battery. So in that condition, they go to generate that electric current or electricity, or they convert into the light energy into electrical and useful electrical energy. So that is the concept of photodiode, and the symbol is given here. The next slide, you go to see the symbol. Okay, that is a whether you go to see this type of devices here. Yes, say yes or no.
Yes, sir.
Eh? Yes. So where they are using, any ideas?
Sir, they are usually used in circuits.
Circuits. Okay.
Indicator as an indicator.
Indicator, the detector, sensor. Okay. So many cases they are using photo sensors, photo detectors. Okay. So especially these are made up of silicon, germanium, see the indium, gallium, arsenide, and phosphide, and indium gallium arsenide. So these are the combinations they are using. Okay, for photodiodes, and it sometimes it also using as an optical filter, and this built-in lenses on the surface area where the area of the photodiode increases. That it depends. Okay, and it is more response time. That is more and more photons that they go to strike. Okay, so the area increases. What happened? Definitely the light energy go to strike that the surface is also increases. So due to this, the number of photons they go to strike is also increases. Okay, so that concept only you go to take it here. And a few photodiodes will look like a normal LEDs. That LEDs. Okay, so this they mentioned here. There are two terminals. So one is anode, other one is cathode. Okay, there are two. How you go to differentiate? The smaller terminal is cathode, and the longer terminal is acting as an anode like that. That is positive negative combination. Cathode and the anode. That is one pin is that compared to the length. One is very high lengthy, the other one is too small. Okay, and now you go to understand which one is anode and which one is cathode like that. So this is the basic diagram. Then what about the symbol? How they go to convert? See the one more diagram here. So anode and cathode is there. So light energy go to strike. Light energy go to strike the surface here. Where see the surface on the top surface. When the PN junction is illuminated by a light or a photon of energy h nu light. So definitely that is made up of photons. There is no doubt, and the energy is also there. Energy is greater than the band gap. Okay, simply these photons are absorbed in the semiconductor and electron hole pair generation. That working concept we will discuss now, no problem. Okay, generated both in N region as well as in the P region of the junction, PN junction. That concept I will explain. So how it is working, the photodiode. Okay. The next is working concept of photodiode. How that working? See here. The first case, the electron hole pair generation takes place, and second, how they go to recombine, how the energy is coming. Okay, one by one you go to see. For first, the electron hole pair to contribute towards the current in the external circuit, and the generated electron hole pair must be separated before they go to recombine. So when the light energy go to strike, see the here, when the light energy go to strike, okay, what happens initially? Anyone? See now that is a PN junction here. When the photons of energy go to strike, okay, or simply they go to reach the surface. So definitely what happens? The electrons gains the energy, then simply they go to leave from the valence band. So due to this, the holes are generated. Is it correct or not? Say yes or no.
Yes,
Yes.
sir.
Yes. So that electron hole pair to contribute towards the current in the external circuit, and this generated electron and holes must be separated before they go to recombine. Because why they go to recombine means simply the lifetimes of electrons in conduction band, that excited state is too small. Simply they go to come with where again they recombine with the holes. Okay, that energy electron hole combination takes place. Where in so many regions are there. Okay, so yesterday we discussed. So when the PN junction is formed, so definitely exactly at the center, the potential barrier is there. So that is built-in potential is there. That is VBI. I think yesterday we discussed. Please remember that concept here. And the electric field in the built-in potential or the contact potential sweeps away the electron and holes in the opposite direction, and they go to prevent the electron hole recombination also. Sometimes. And the photo generated minority carriers, which are generated within that diffusion length from the depletion region, can also diffuse to where the same depletion region without a recombining. So the concept is there, and they are stepped across the junction due to this electric field present in the depletion region, and due to the direction of electric field being from the N region to P region, and the holes, definitely the holes will flow towards the P region, and electrons almost moving towards the N region. So the direction of this photo generated current, see IL, that I suffix L, I is nothing but the current. Okay, so here that photo generated current IL is opposite to that in the forward bias diode, because that is in the reverse bias condition only they go to take, and the total current is given by that IL is equal to IN of L plus IPL plus ID. The three combinations are there. Okay, so due to electrons and due to holes and due to that carrier densities. So I suffix N, so that is current due to electrons, N type. And so I suffix P, that is current due to holes, and plus ID, the concentration of the materials. Okay, so these three combinations are there. That IL is equal to INL plus IPL plus ID. Okay. Yes. Then you go to see the diagram here. Based on that, I go to explain more. See, when the photons they go to strike the light energy, that is incident photons, light energy they go to strike where in the PN junction region, in the PN junction region here. See, the PN junction region. Okay, definitely the photo current. How the photo currents are generated. So very simple. See here. So once the light energy go to strike, simply is eliminated. Definitely they go to break the covalent bond or ionize, and this generates electron and hole pairs, and the photo currents are produced where due to the generation of this electron hole pair, electron and the hole pair. The electron hole pair are formed when the not all the photons of having energy more than 1.1 electron volt go to strike the photodiode. So that is a threshold value. Are you understand this? Say yes or no. Yes.
Yes, sir.
Yes, Mo. I can't understand. Yes. Are you understand this concept or not? So the electron hole pairs are formed when the photons of energy greater than, please note it down, that is 1.1 eV electron volt. It's the diode. And the photon enters where? In the depletion region. So see here, the dotted lines, the depletion region is there. So depletion, the width of the region is almost wider here. Why? What is the reason? So why the width of the depletion region is more? What is the reason here? Anyone? I think yesterday we discussed. See in the diagram, you go to see here, the dotted lines are there. So these both sides the dotted lines, that is the width of the region, in both P type and N type. So why the width of the region is increased here? Depletion region. What is the reason? What is the reason? Anyone? Yes? See whether I'm audible or not.
Yes, sir.
Audible. Then what about the answer? So why your width of the region is increased here? What is the condition? You go to see the diagram and tell me. I think the answer is same in the diagram itself. Anyone? See, P is connected to where? P is connected
Negative
to
terminal.
Negative terminal.
N is connected to positive. What type of biasing? This is forward bias or reverse bias?
Reverse
Forward
bias.
bias.
Reverse bias.
Reverse bias. There is no doubt. Definitely, when the PN junction is connected to reverse bias, there is no doubt width of the region goes on increasing. Is it correct? Yesterday we discussed. Yes.
Yes.
Are you remember? So due to this, that why you go to take? At least you go to prevent sometime that electron hole recombination does not take place. So that is the reason. See here that they go to generate. When the photon enter into the region, that region, depletion region, it hits the atom with very high energy, and this due to this, the electron from the atomic structure can simply they go to release. So after that, the electron releases, the free electrons and the holes are produced. So that concept is there. When the photon go to strike, there is no doubt each photon having certain amount of energy. If that photon having the energy is greater than 1.1 electron volt, there is no doubt. But definitely these photons they go to share the energy with the atoms. Simply the electrons in the atoms gains the energy and goes to the excited state, the conduction band. So the electron holes are produced. That is carrier generation. You say this is carrier generation. That is one type by using the photons. There are four type of carrier generation already you studied here. That is the one type. Okay. Then the electron have the negative charge. Okay, leave it that the amounts of the positive charge. And the depletion region will have built-in electric field, that is VBA plus VF. Due to that built-in electric field, electron hole pair moves away from the junction. Please understand, moves away from the junction. Once the holes move to anode, anodes is moving towards because they are positive, and electrons moving towards cathode to produce the photo current. And this absorption, photon absorption intensity and the photon energy are directly proportional to where? Both are directly proportional to each other. And the energy of photons is less, definitely the absorption will be more like that. And the entire process is happened where? Inside the depletion region. You say that is inner photoelectric effect. Inner photoelectric effect. I think you know what is the meaning of photoelectric effect. Yes? What is photoelectric effect? Yeah. Anyone?
When light incident on metal
Yes.
electrons or something like that.
Liberated metal surface. So this happens where? So that is in the metal surface there. But here this is happened in the where? Depletion region. That is in the PN junction diode. PN junction diode, especially where in the depletion region, you say that is inner photoelectric effect. Inner photoelectric effect. Are you understand this concept here? Yes? Okay, okay. Now you see how that photo current next. In the diagram they go to explain energy band diagram. Okay. So yesterday also you discussed that EC, EV is there in between EI. I think they removed all these things. So now how they go to take here? The different diffusion takes place. The first you go to see here. The diffusion is coming both N and P regions here. There is a homogeneous P region and this is homogeneous N region. So N and P regions are there. P type and N type junction. So N and P region. In between the depletion region here there, that is a width is also given here. See W is the width of the depletion region, and L, that is a photocurrent generated IL, is also given due to electrons and the holes. See here the electron diffusion region and the here holes diffusion region. The corresponding E I go to take here LE and that is LH here. You understand? Yes? Say yes or no. Say yes or no, yeah?
Yes,
One
sir.
question.
Yes, sir. Yes, sir.
Okay, so this photocurrent, then due to the combination, so both the diffusion and drift is also there. See here, that is a diffusion process here, electron diffusion region. And similarly here, that also diffusion region in N side and the P side, that is electron diffusion region. So this is PN junction. So that is given here, PN. So see here, that the region up to this is PN region, PN junction region. So here the photons they go to strike. So here the photons can leaving now there. That's all. Okay, they recombine with the majority of electrons before reaching the junction. And similarly here also holes. They go to recombine with H plus before reaching the junction like that. And this is due to diffusion process. And here that is a drift process is also there. Some small amount of drifting is also there. Okay. And electron region, holes region, that is Le and LH. So that is in the formula that IL. Okay, how the currents are generated here. IL, photocurrent. Then one more diagram. So how, where they go to generated here. So photocurrent. So there are three regions. So first one is the built-in potential. That is a spacer region. And second, where the photocurrent generated or the photo generated current in N region and P region also. If G is the rate, the generation rate of excess carrier, and the A is the area of the diode area, the excess carrier in the depletion is quickly moved by the electric field. That is the electron to N region and the holes to P region given here. See here in the diagram. So this is the width of the region. P is connected to negative and N is connected to positive. The light energy go to strike here. See that the W, nothing but a photon H nu is there. Each photon of H nu go to strike where in that depletion region. So that the process already I told. Okay, the electron hole pair generated like that. Okay, and this G, how you go to calculate? See the generation, the rate of generation, the photo generated current. So in that the depletion region is given by that equation I is equal to AE integration of G into dx, or that is equal to that AEG W. W is nothing but the width of the region here. That's all. Where W is the depletion width, and this is current is very fast. That is, you say that is a prompt current or a photo current. The width of the region, W is the depletion width, and this is the very fast. In addition to charge carriers generated in the depletion region, the electron hole pair generated where? In the neutral N and P region also. Not only the depletion region, N side as well as P side, that is neutral. At the N region and the P region of the diode also. Okay. So yes or no? Can you understand this or not? Yes? Yes. Then come to the next one. So now how are you going to express this equation? See here, when the holes and electrons are generated, that is LP and LE, within the distance L, okay, or the depletion region edge, and will be able to enter the depletion region from where the electric field is swept out. That is IP and IN is also given. That is E, G, LP, A, like that. You go to see here also E, GL, LN, A. This is IP and this is IN. So excess electrons and excess holes are also generated. The corresponding current is given here, IP and IN. That's all. Okay, this is current due to holes and this is current due to electrons. So E, I think you know that is a charge. GL is nothing but the gain. Okay, here. And L is a region, width of the region. A is the area of cross section. A is the cross section. Okay. Yes. Understand? See, understand or not?
Sir, what's G?
Gain, that is a expression. Just now I told no. So the rate of generation, GL. See here. Rate of generation or excess. G is the generation rate or excess of charge carriers, electrons and holes. See, due to when the photon go to strike, what happens immediately? The electrons and the atoms gains energy from photons, and then they go to leave. That is electron holes pair generation. Electron hole generation takes place. That rate is given by G, rate of generation or generation rate of excess charge carriers. So that is given by this equation. That is given by this equation here. See, that is E, GL, LPA and E, GL, LNA. So that is identified in the diagram here. You go to see the diagram here. So this region is there, LN, LE, width of the depletion region W. This is PN region, active region, and this is the width of the region. And this is a different diffusion process where the different diffusion process takes place. So all these things is explained by this diagram only. Based on that only you go to write that IP and IN. That's all. See that equations. EGL, LPA, here LNA. That's all. So what about LP and LN? Anyone? Yes? P and N is okay. That is nothing but the holes and the electrons. So that is a with a length where how long it will be take. That is the region is given here. LP and LN like that. Okay. Yes. See, are you understand this or not, Ma? Whether you understand?
Yes, sir.
Yes, sir.
Yes. Next. That combined. So the total current due to the carriers. Now I go to add all these things. The neutral region and the depletion region is given by this equation. That is overall IL is equal to E. You go to take that EGL common for outside. That LP, LN, W and A. A is nothing but area of cross sections here. W is the width of the region. LP, LN is also there. You please go to see the diagram. Okay, up to that PN junction. See here. This is L is there. LP is also there. See here. That is LE. So that is here. LN almost that is called LN. This is L holes LP, and this is W. So now I go to add all these three regions. So that entire region is covered by that PN junction here. See, that is the active region. So LE, plus W plus LH. That whole, all the three regions you go to combine, that is PN junction, PN junction. Okay, that is active region, width of the active region like that. So that is explained here in the diagram. That's why they mentioned here. So when the excess charge carriers, electrons and holes are generated, how much amount of current will produce, that is also given here. And what is the total current is also given, mentioned here. This the dial is equal to, I go to take E, GL common outside, and write for LP plus LN plus W. They mentioned here, see here, that electron diffuses Ln, and the width of the region, see here W, and this is hole diffusion LP. You go to add all these things, LP plus Ln plus W. Okay. Yes. See whether you understand this photo current concept or not. Yeah, photo current. Yes. Photodiode. Are you understand or not? Yes or no? Yes. Yes. So I think this is your last slide. More up to this, you go to stop. Okay. So this is the total current gained by where the collected that regions carriers. Okay, in the neutral region, and depletion is also sometimes you go to take into a depletion region also. Any doubts or clarifications here? Yes. See in the photodiode, any doubts or clarifications in photodiode? Huh? Say yes or no more. Okay. See, I understand. All of you understand this? Yes, say yes or no.
Yes, sir.
Yes, sir.
Yes. Okay, then I go to stop the share screen. Please wait. I will come to the video mode. Okay, that full video. The attendance purpose. Okay, just wait. I will come. Okay, ma. I think so. Now you understand. Yes. Say yes or no. Understand the
Yes, sir.
the optoelectronics.
Yes,
See,
sir.
first you see what are the materials used for semiconducting combination. Semiconductor is for optoelectronic devices. Second, you see what is photodiode. How that for working concept. What is the basic principle and what is the working principles of photodiode, and where they are using like that. You go to study. So that is your lecture 13. Semiconductor applications of the for semiconductor materials for optoelectronic devices. Then this photodiode concept. These two topics. Any doubts or anything else more here? Any doubts or anything regarding this?
No, sir.
No. Okay. So okay, please just wait here. I go to take attendance. Please carefully give it attendance. After that, you go to discuss any doubts or clarifications. Again, I go to check. No problem. Okay, come to attendance part. What about 51,
Present.
52,
Present, sir.
53, 53? Okay, chat box. Okay, 54.
54 present, sir.
Okay, 55,
Present, sir.
56. I think it's not there. Ashavardhan is left. 57,
Present, sir.
58,
Present, sir.
59,
Present, sir.
60,
Present, sir.
61,
Present, sir.
62,
Present, sir.
63.
Present, sir.
Okay, 64. I think 64 is not there. He is also left. 65. 65. I think it shows absent. 66.
Present, sir.
68. 68 more. It's not there. Okay, 69. 68. Wait. 53, 69. Yes, okay. Just wait. Okay, 69. 70,
Present, sir.
71, 71. 71 is there or not? It's not there. Okay. 72,
Present, sir.
73,
Present, sir.
74, 74, 75,
Present, sir.
76, 76.